Gdańsk Colloquium. Our speaker today is Boban Velickovic from University of Paris Cité. I know that the other things are too complicated, so he's just from University of Paris.
Great, thank you very much. It is a great pleasure to be here and to see that set theory is flourishing in Gdańsk. So I wanted to tell you about higher forcing axioms, but I don't know your background. So I'm going to start from very basic things and slowly move up to what we are working on. I won't prove much, but I hope to give you an idea what the subject is, why we're doing it, and what are the difficulties. So in search of higher forcing axioms, so the 4 parts of this talk. So first, maybe it's kind of silly to tell you about this because it's just a very basic introduction about the set theoretic universe and the axioms that are supposed to describe it, the ZFC axioms. Now, as you all know, there are many mathematical statements that are undecidable on the basis of these axioms, and I just listed a few. Of course, the most famous is the continuum hypothesis, and maybe Suslin hypothesis. There is no particular reason for mentioning. Just the things that I thought are the best known. So if you complain that there are only set theoretic statements, the Whitehead's problem is an algebraic statement, and Kaplansky's conjecture is was a problem in Banach algebra. Okay, so what do we do when we run into undecidability? Well, we can just shrug our shoulders and say, well, that's life. We just keep proving consistency results, and that's it. But if you believe Gödel, we actually can have another attitude. That is that the axioms we have isolated so far just give us a partial description of the set theoretic universe, so we are just missing some axioms. Now, you could argue that the Gödel's incompleteness theorem says that we cannot possibly have a complete set of axioms, and that is fine, but we could have some kind of hierarchy of axioms that decide more and more statements, and eventually every statement or every reasonable statement could be decidable in this hierarchy of axioms. So it is now called this program. I don't know if Gödel himself proposed, he did mention this, but whether he actually proposed this program. So the basic idea is to search for new axioms for set theory. There has been a lot of philosophical discussion that I don't really want to get into, like the multiverse approach and various philosophical approaches. I'm just going to be very traditional and just say, no, we're just missing some axioms. So how do we go about supplementing the axioms of ZFC? So the two main lines of research are the large cardinal axioms. Here, I actually include the determinacy axioms here that provide a linear hierarchy. Actually, that's what we think. I don't think we even have a definition of what is a large cardinal axiom. Do we have, Rico? There are some attempts, but I don't think we all agree on what is a large cardinal axiom. So it's hard to prove a theorem without having a definition. But we have, I call it a dogma. One of the dogmas in set theory is that large cardinals are linearly ordered and linearly ordered by consistency strength and every theory can be measured on the scale. It's actually, this is not even true. But I think we don't mean the actual consistency hierarchy, we mean something else, maybe omega in omega logic. Anyway, so, but we're not going to go into that. The other is, now large cardinal axioms, they decide certain things. I mean, say the second order theory, second order arithmetic, but they don't decide the continuum hypothesis. So another approach is forcing axioms. Now, if you want to speak vaguely, large cardinals talk about the height of the cumulative hierarchy, and forcing axioms talk about the width, at least at the low level. Again, this is not a precise, don't take my word for it. Just, okay, so the idea is to say that the power set operation is not sort of determined enough. So we express the kind of intuitive idea that all sets that could possibly exist already do exist. Now, when I say it, it's not quite, doesn't even make sense. So try to make sense out of it. Okay, so of course, these two types of axioms are very closely intertwined. And typically, you need large cardinal axioms to prove the consistency of forcing axioms. Now, let me tell you a little bit about classical forcing axioms. They're usually stated as asserting that certain for a certain class of partially ordered sets, or if you like, complete Boolean algebras, for class K, and every partial order in K, and the family of kappa many dense sets. So kappa is a parameter, it's an uncountable cardinal. There is a filter in P which meets all the dense sets in D. This is a traditional form of forcing axioms. So you can think of the case kappa equals L0 is just the bare category theorem, which is provable in ZFC. So the first one is Martin's axiom. So it's this axiom for partially ordered sets which have the countable chain condition. And that means that if you have an uncountable set of elements of P, then there are two that are compatible. Compatible means there is a third one that's stronger than both of them. So this axiom was isolated by Martin and Solovey, essentially from the Solovey-Tenenbaum proof of the consistency of Suslin hypothesis. And they proved, so this is the first forcing axiom. They proved that for an uncountable cardinal, with 2 to the less than lambda is lambda, there is a generic extension in which Martin's axiom for fewer than lambda many dense sets. And continuum is equal to lambda. So, I mean, now we're in the 1970s. Here are a few consequences of Martin's axiom. I think you all know them. So they do not settle the value of the continuum. I mean, but MA, Martin's axiom for kappa many dense sets, implies that 2 to the omega is equal to 2 to the kappa. So in some sense, kappa is close to omega, quote unquote. For example, the union of kappa many Lebesgue null sets is Lebesgue null, the union of kappa many meager sets is meager, etc., etc. And here, for example, for MA Aleph 1, I just wrote a few well-known consequences of MA Aleph 1, but this is where the Whitehead problem is. One direction of the Whitehead problem is answered, and the other is under diamond, or some strengthening of diamond. Okay, so this is all very well known. So now let's move quickly to stronger forcing axioms. And So the reason for studying them is that, of course, Martin's axiom doesn't decide many questions. I mean, many questions are not decided, in particular the value of the continuum, but also many other combinatorial statements. And so this motivated the study of stronger forcing axioms. So what does it mean? Stronger forcing axioms, well, include a larger class of partially ordered sets. And among those, these are really the very classical ones, are the proper forcing axioms. So this is the forcing axiom for, I will actually write down, I have the definition of proper forcing in the next slide. For Aleph-1 many-dense sets for the class of proper partially ordered sets. SPFA is the same, but for semi-proper posets. Martin's maximum is the same for stationary set preserving. So that means posets that preserve stationarity of subsets of omega 1. And it turns out that this axiom, these two are actually equivalent. Because under this axiom, SPFA, all stationary set preserving forcings are semi-proper. So the two classes are not provably the same, but under this axiom they are. Okay, so here is the definition for those who have not seen it. If you're taking notes, I can slow down. Do you want me to slow down a bit, or?
It's recorded, so.
Oh, it's recorded. Okay. So the a poset P is proper if for every, so you have your poset for every theta large enough. Basically, you want the power set of P to be in H theta. Remember, H theta is sets whose transitive closure is size less than theta. So for every countable elementary submodel of H theta, which contains the poset, and given a condition inside, the condition is an element of P inside the model, there is a stronger condition, which is typically outside of the model, which forces in this poset P, that n of G, so what is n of G? You just take P names which are in N, and you evaluate them using your generic. Intersection, the ordinals is N, or if you like, V, the ground model. So basically, N of G is the interpretation under G of all P names which are in the model N. And this says that Q forces that this doesn't, N of G has no new ordinals compared to N, or even you can say V. Here you could say V, the null model. Okay, so such Q is called NP generic. And so this is proper, and semi-proper is almost the same, but you require less. You require that only N of G intersection omega 1 is the same as N intersection omega. So you don't add any new countable ordinals to N. When I say I don't add, and what I mean is you take N and you interpret the P names which are in N by your G, and you don't get any new countable ordinals. Okay, so these are all classical definitions, so I won't spend time. So this is the beginning of this was a theorem of Baumgartner, Schellach. I think Schellach really proved it, but Baumgartner formulated it or something like that. That is the consistency of PFA, the proper forcing axiom, using a supercompact cardinal. And then a few years later, I don't know if this 88 is maybe the year where the paper was published. Foreman, Magidor, Schellach showed the consistency of Martin's maximum. So this is the, and why it's called Martin's maximum, because it is the provably maximal forcing, in the sense that you cannot have it for, cannot have the forcing axiom for any forcing which does not preserve stationary subscript of omega 1. So it kills the stationarity of a subscript of omega 1. Okay, so here are some consequences of PFA. Again, these are all classical results from the 80s. This actually was proved before PFA was even formulated, in a way. I mean, it was not proved. I mean, Baumgarten proved the consistency of this statement that every two Aleph 1 dense sets of reals without endpoints are isomorphic. He proved the consistency, but once you know the proof of the consistency and you know PFA, you say, well, okay, so that gives you that PFA implies that. Some other consequences are there are no Kurepa trees on omega 1. If you don't know, a Kurepa tree is a tree of height omega 1, which has countable levels, but has many branches. More than omega 1 branches. And then some properties about trees, higher trees of height omega 2, no Aleph 2 Anoshain trees. So what that means is that an Anoshain tree on kappa is a tree of height kappa whose levels are size less than kappa and has no cofinite branches. So here it says that it's a kind of compactness here. No Aleph 2 Anoshain trees is a weak compactness minus inaccessibility. You can say it like that. But another thing is that I mentioned in the beginning Kaplansky's conjecture, which is a more mathematical statement. And people can say, well, these are all set theoretic statements. What about real math? So there are some real mathematical statements that are decided by the proper forcing axiom. So one is this Kaplansky conjecture. This was proved by Woodin in his PhD thesis. For every compact house of space, every homomorphism of the C of X is the continuous functions on X, real continuous functions on X, to any Banach algebra is continuous. So you have an algebraic property, it's a homomorphism, and from that you deduce a topological continuity. Okay. So some structural consequences are you get the continuum is equal to Aleph 2. So that gives you some strong consequence of. So this, remember, this was not, Martin's axiom does not decide the value of the continuum. And here you do get the value of the continuum is Aleph 2. You get singular cardinal hypothesis. And you get the failure of square principles at various regular successor square sub kappa for all kappa bigger than equal Aleph 1. So from this you deduce that consistency strength of PFA is very high. So these are structural consequences about the set theoretic universe that PFA gives you that you didn't get from Martin's axiom. Martin's axiom is a very weak axiom. Now you may say, why are you telling us all this? We know these are all results from the 80s. Well, because we are going to try to generalize. Remember, we are in search of higher forcing axioms. So we start with these principles and then we try to find some analogs of these principles higher up. Just a couple more structural consequences. So I wanted to include some consequences of Martin's maximum, which do not follow from the proper forcing axiom. And one is the saturation of the non-stationary ideal. So saturation means that the Boolean algebra, power set of omega 1 modulo this ideal, has the Aleph 2 chain condition. Then you have Chang's conjecture. This two cardinal transfer principle. And another result that I wanted to mention, but I don't have many connections and extensions of these two higher forcing axioms. It's just mentioned. So that from Martin's maximum delta 1, 2, so which is the supremum of lengths of delta 1, 2 pre-well orderings of the reals is equal to omega 2. Okay, so I just wanted to refresh your memory about some classical results. So what about higher forcing axioms? First of all, why do we want them? So it depends on your, what is your motivation? I'll tell you what is my motivation. I think that classical forcing axioms are very nice, very useful. They give a satisfying theory about sets of size aleph 1, and not necessarily just the power set of omega 1, but omega 1 sequences of say, ordinals or something. But in a way, they're local axioms. They don't tell you much about power set of omega 2. So we should explore what can you do, some kind of analogs of this, and if you want to argue that these axioms are the right axiomatization of the set theoretic universe, a philosopher could argue, well, but they only determine power set of omega 1 essentially. So we should at least explore the possibility of having higher forcing axioms. But we have to agree what we mean by it. So the first approach is, and this was actually studied already in the 70s. What is a kind of analog? So you have a forcing axiom for meeting aleph 2 many dense. Well, you already have Martin's axiom. You can meet kappa many dense sets for, MA kappa is consistent for arbitrary large kappa. However, the problem is that, as we saw, MA kappa is rather weak. It doesn't decide any structural properties of the set theoretic universe. So I particularly wanted to draw your attention to this. Continuum is equal to aleph 2 from PFA. Continuum is equal to aleph 2, the singular cardinal hypothesis, and the failure of square. So these are structural consequences of PFA. So you don't have anything like that from MA. So in some sense, it's a weak axiom. And of course, it's consistent. It doesn't require any large cardinal. So we want to formulate some axioms for meeting, let's say, aleph 2 dense sets. But they should include larger classes of posets, not just the countable chain condition. Or maybe we don't have all CCC posets, but we have some other class, but we want to have some structural consequences. So let me tell you that, there was some work on higher forcing axioms, even in the 70s, where people said, well, why don't we generalize Martin's axiom to aleph 2 CC posets, but countably closed. So countably closed means if you have a decreasing sequence of conditions, there is a lower bound. And there was quite a bit of work in the 70s. It turns out that things are quite delicate. If you just say aleph 2 CC sigma closed, this axiom is just false. Then you can actually strengthen aleph 2 CC to something like regressive aleph 2 CC, whatever. I don't want to tell you the definition. And even sigma closure should be strengthened. And then, so there was some work of Baumgarten and Sherlach and Stanley and so on in the 70s, late 70s. Unfortunately, that axiom was quite weak. So it's even weaker than somehow we were trying to get some structural consequences, and there was no such thing. Okay, now let me tell you what the obstacle was. The main obstacle was that we didn't have good iteration theory for iterating large classes of partial orders. We have finite support iterations. They preserve CCC posets. So if you do a finite support iteration of CCC posets, you get a CCC poset. Then there are the countable support iteration. They for proper posets. So when you do a countable support iteration of proper posets, you get a proper poset. And then there is a kind of extension of it called revised countable support. So this was defined by Scheller. Countable support, I don't know who defined it first, but it's kind of the obvious thing. Revised countable support is not at all obvious, but it was defined by Scheller, and he used it to iterate semi-proper posets. So in all these, according to the class of posets, we use one of these iteration schemes or techniques. Then we also have to iterate up to some cardinal. In the case of CCC, we don't need any large cardinals. In the case of proper and semi-proper, we need some kind of diamond principle, Laver diamond. Okay, now, but what was the obstacle? I mentioned that there was an obstacle, and the obstacle was that, first of all, finite support iterations do not work for non-CCC posets. Namely, if you do even like a length omega iteration of non-trivial non-CCC posets, you will collapse omega 1. So, and we typically don't want to collapse cardinals. That's the problem. And that's one thing. So on the other hand, the countable support and revised countable support iterations, the proofs that the iteration of, say, countable support iteration of proper poset is proper and therefore preserves omega 1 relies on some kind of diagonalization. I don't want to go more into it, but the diagonalization is a countable diagonalization and supports a count. There is a lot of work by Scheller and Roslanowski where they look at uncountable supports, but they require the individual posets to be highly closed. So that's not what we want in this context. Here we want continuum to be large, and in that case, continuum is Aleph 1. So you see, the problem with this diagonalization is that you can do it for one cardinal. If you use countable support, you can do countable diagonalization, and you can prove the preservation of omega 1. But you cannot have two diagonalizations for one type of support. So there is a kind of, it's too much, the proof of the preservation theorem is too much tied to the size of the support, and you can do only one diagonalization for one cardinal. You cannot do for two cardinals. Now you can, in all these iteration results, I mean, you will preserve omega 1, and you will typically, for example, in the proof of PFA, start with a very large cardinal that you will preserve that cardinal, it will become Aleph 2. But here you would like to say preserve Aleph 1 and Aleph 2 and go up to some inaccessible cardinal, and that cardinal becomes Aleph 3. Okay. So some work, well, not so recent, but the major breakthrough was the realization of Ita and Niemann that you actually can decouple the proofs of iteration and support by using side conditions. And I'm going to tell you a bit more about side conditions later. So he gave the new proof of the consistency of PFA. But the point of this is that this opened the door to higher forcing axioms. So far, we don't know what we're looking for, but I'm just telling you this at least gives us the possibility to formulate and prove the consistency of higher forcing. Also, Aspero and Mota have done a lot of work with side conditions, not somewhat different. For example, they have a class of forces that they call Aleph 1.5 cc, and they use some symmetric systems of countable elementary submodels of some suitable h theta to iterate such forcings and get the consistency of the forcing axiom Fa kappa for this class. So this is a somewhat bigger than CCC, but less than proper. No, I mean, properly included in the class of proper. And they have the consistency of this axiom for arbitrary large kappa. Also, John Kruger has a framework of for forcing with adequate systems of countable elementary submodels, again, as side conditions. I don't know, I haven't seen any general iteration theorem, but he adds lots of objects of size Aleph 2. So, okay, I'm not doing justice. I mean, there are lots of many more people. But, okay, so I was working actually on trying to adapt Itai's Niemann's approach of side conditions to iterate semi-proper forcings, and I realized that one has to, normally one uses countable elementary submodels of some h theta as side conditions, and after struggling for a long time, I realized that you have to allow more models, not only countable elementary submodels of various h thetas. And this led to the definition of virtual models. Now, virtual model is actually an actual model, but the reason I call it virtual is that it's not elementary submodel of some fixed h theta. So typically you use something like this. You actually allow, so I don't know, you, no, I'm just, M has some small things, some countable ordinals, and then has some higher things. I mean, this is all M. Right? This is the usual countable elementary submodel of some h theta. But if you try to iterate semi-proper forcings, that is a problem. And I mean, the reason is that basically, I mean, even Niemann's proof of the iteration of proper is not an actual iteration. It's something like you start with the side conditions, which are models of two types, and then you fold in working parts, but it's not an actual iteration. In other words, you're not saying that if you say at stage alpha, the positive is P alpha, and at stage beta is P beta, it's not the case that P alpha is a complete suborder of P beta. It's more like you fold in some sense. And if you, and this doesn't work if you want to do semi-proper iteration. So that's the problem. Now, the idea of virtual models is very simple. We will do an iteration up to some inaccessible cardinal kappa. Let's say this is V kappa. We index the iteration not by all ordinals less than kappa, but only by a certain ordinals. So that's the set E. So what is E? Well, these are the alpha such that the V alpha is an elementary submodel of V kappa. Okay, kappa is inaccessible. So there are many such alphas, and it's a club. And this is just to avoid too much indexing. So this is not a big deal. Now, when we are at stage alpha, we want to use somehow, and this is the issue that that you have in Niemann's approaches. You want to use all models, elementary submodels, all the way up to kappa as your side conditions in the construction of the next post. So you go all the way to V kappa, to kappa itself. And that's a problem. Now, instead, what we do is essentially the idea is the following. You have two models, M and N. And I want to say, for me, a model is, while we discussed this with Grigor the other day or yesterday, in people in the model theory, they always take transitive collapses. And in forcing, people never take transitive collapses. Why? Because for us, for people doing forcing, a model is not really a model. It's a container of information. And so the fact that M and N are isomorphic doesn't mean too much. I mean, okay, so they have the same transitive collapse, but they don't contain the same objects. And in particular, I'm interested in the kind of information that M and N have over V alpha. And this is expressed in the following way. So I want not only M and N to be isomorphic, but I want that if I add V alpha to M, so this is the half of M together with V alpha, this is isomorphic to N with V alpha.
How is computed in V kappa?
Hmm?
You compute the whole in V sub kappa?
No, I'm going to tell you in a second. I don't mention V kappa. So what is the HAL? This is just the set of all f of x in V alpha, and f is in n. So I just take functions in the model M. I don't need scalar functions. So you just take functions which are in M and evaluate them at tuples which are in V alpha, provided this tuple is in the domain. Basically, I would like to say M and N are alpha isomorphic if, I'm just writing, if there is such an isomorphism which maps M to N. So, being alpha isomorphic, it's more than being isomorphic. Somehow they're isomorphic, and in some sense they contain the same information about V alpha. Now, it turns out that you can actually represent, so this gives me obviously an equivalence relation. And then we want to use equivalence classes as our side condition. But it's too complicated to use equivalence class. So what we do is we say, but look, what I can do is I take the HAL of M together with V alpha, and now I take the transitive collapse. So I take the HAL of M V alpha and then take the collapse. So let's call it HAL bar. And then I take pi of M. So this is sort of pushing M down. I mean, the part below, M has some part below alpha. Has some countable ordinals, reals, blah. This doesn't change. And the part about V alpha just gets pushed down to V alpha. But then actually, if two models are alpha isomorphic, they have, this is called the projection to alpha. They have, you can actually define the alpha isomorphism to say, project them to alpha in this way. They have the same projections to alpha. So rather than talking about equivalence classes as side conditions that just add these models, they are now, what are they? This model here, half of MV alpha, is an end extension of V alpha It's actually an elementary end extension. And M, this model, or M projected to alpha, which is the same as this, is an elementary submodel of not of V alpha, but of elementary end extension. Okay, so we use these models as side conditions. So this, but once you have this, one of the key features of the Niemann side condition method is that side conditions in his case are epsilon chains of models. It could be just countable models, or maybe models of two types, countable and transitive, etc. But this doesn't work if you use these models. What you want is that, you know, if you have M, now an element of N, you project to alpha, maybe M alpha is not an element. It could happen. It's not an element of N projected to alpha. But it's going to be, so we have to introduce another relation, epsilon alpha. It's basically saying that, remember, these models are not actual models. They're, if you like, they're models, but they are representatives of equivalence classes. And so here I would say M is an epsilon alpha N if there is some other model which is an actual element of N, which is alpha isomorphic to M. So that the equivalence class of M is represented in the model N. Then, okay, so this is the easiest thing. I mean, this is a very kind of basic thing. So you have some notion of isomorphism, which is, as alpha increases, it's harder and harder. I mean, if alpha is equal to kappa, then being alpha is just being identical. So this is demanding more and more. And then you have some notion of epsilon alpha. Now it turns out that this is actually, it makes the whole iteration theory very smooth and very easy. I mean, the proof of the properness, proof of the semi-properness is not so easy, but it's kind of, once you know how to do proper iteration, then you know what you have to do to iterate semi-proper. There are lots of steps, new steps, but somehow once you have the right definition, then you know what to do. So it's not too bad. So there are several advantages. So the main advantage is that there is no need for transitive models. So in Niemann's approach, he uses two types of models, countable and transitive. Here we use only countable, but rather than taking only countable elementary submodels of some V kappa, we take these generalized models of virtual models. And our conditions, if you just want to do the side conditions, they're going to be finite collections of these models, such that for every alpha, if I look at the models that are active at alpha, I have to tell you what active means, but somehow that are relevant to me, then they form an epsilon alpha chain. Now I have to tell you what active means. Basically, well, I don't want to tell. Maybe, I mean, because you will get, we'll go to some more general things. So I will maybe mention it later. Okay, now you can iterate other classes of positives. Now I don't have a good iteration theorem, so I can reproduce like Shellax iteration results for some classes, but so far no general iteration theory. I don't think there is a, we know that you cannot iterate all stationary set preserving forces. So, but there could be a nice, reasonable class of stationary set preserving forces which we could iterate. Now, what I wanted to talk about, and this is the main point of today's lecture, is that now we can try to do forcings preserving two cardinals, let's say Aleph 1 and Aleph 2. by using two types of models. For example, we could use countable models and models of size Aleph1. And then, our gain over Niemann is that Niemann had to do two types of models just to iterate proper. And if you want to iterate this generalized proper for omega 1, omega, etc., so preserving two cardinals, omega 1 and omega 2, you would need three types of models. Now here we did proper, with one type of models. And so we can do two types of models, but these virtual models as side conditions. And then we see what we can iterate. Now, it's very nice to say it, but when you actually start to work out, there are lots of difficulties, technical difficulties. So one thing that was very important for Niemann is that when he uses two types of models, is that this collection of side conditions have to be not just epsilon chains, but they are closed under intersections. So in other words, if you have a big model, uncountable model, N, which is an element of a countable model, M, then if you put both of them on your side condition, then you should also put N intersection M on your side condition. And there is a reason why. I mean, I don't want to spend too much time on this, but this is somehow necessary if you want to have both models. Now, if you only have models of one type, then there's no need, because if N is epsilon, if N is an element of M, then N is a subset of M. But if they have different sizes, if N is bigger than M, then cannot be a subset. So you have to put the intersection. Okay, so this is fine, but now we are not working with actual models, we're working with virtual models. Again, virtual models are actual models, but you think of them as equivalence class. So we have introduced the notion of an alpha isomorphism and epsilon alpha. So we need some version of intersection, alpha intersection. And this actually is a little bit delicate. So we need some notion of intersection for a big model and a small model. So you have a big model N, which is epsilon alpha M, which is a countable model. Then what plays the role of N intersection M? Remember, N could be epsilon alpha M, even though N is not an element of N. So how you define it? But you can define it, and we call it the meet. Now, it turns out that, I will tell you what the side conditions are. So there are going to be two types of models, countable and uncountable. And what you want is that at every alpha, the relevant models, I haven't told you formally what it is, but somehow the models that can talk about alpha, either, for example, if alpha is a successor element of E, then they have the predecessor in it, or else the model is, if alpha is a limit point of E, then the model is cofinal enough. So somehow this is when we have to worry about the model alpha, about the model M when we are stage alpha. Otherwise, there are models which are bounded in alpha, and they have maybe some stuff above. We don't have to worry about this one. They will not have the composite at stage alpha, and they won't matter for us. But okay, again, I didn't write the formal definition, but it doesn't matter. So so we could use the two types of models where they are, for each alpha, the relevant models, the models active at alpha form an epsilon alpha chain closed under meets. I haven't told you what meets are, but some kind of generalized intersection. There are lots of subtle things, and it turns out that it's better not, so you don't use all models of size alpha, you only use models that have some nice closure property, Or else, and this is what we prefer, is to actually use bigger, not models of size Aleph1, but much bigger models, size less than some kappa, but this kappa will become Aleph, kappa will become Aleph2. So less than kappa will be of size Aleph1 after we do forcing. So we will have two cardinals, kappa and lambda, and kappa will be less than lambda, kappa will become Aleph2, and models of size less than kappa will become models of size Aleph1, and lambda will become our new Aleph3. Okay, so how are we doing with time? 10 minutes? 15? Huh? So I've spent a bit more time than I thought. So guessing model. So actually here, maybe I should say, why am I just sweeping? Okay, this I waved my hands a lot. And now suddenly I'm changing the topic. But it's actually not, because these are the models that we, okay. So this story was about iteration. So basically we have some idea how we want to iterate this class of posets, which preserve two cardinals, Aleph1 and kappa, which will become our Aleph2. So you actually don't preserve Aleph2, but you make kappa into Aleph2, but your iteration goes past kappa, goes to some lambda, which will become Aleph3. Now, here I want to tell you what we hope to get. Okay? What we hope to get is the following. We want some forcing axioms for Aleph2 many-dense sets, and that have structural consequences on the set theoretic universe. By structural consequences, I cannot define precisely what I mean, but think about the continuum, deciding the value of the continuum, implying some kind of cardinal arithmetic, global cardinal arithmetic, a singular cardinal hypothesis, and maybe failure square. So when we try to generalize, to search for higher cardinal versions, we look at some combinatorial principles that follow from forcing axioms like PFA that have structural consequences, but do not imply that continuum is Aleph2. Because those we can hope to generalize to have them with continuum bigger than Aleph2. And there is a very nice principle called ISP, which I will state. And this was formulated by Christoph Weiss and Matteo Viale. So the basic notion is that of a guessing model. So if you take a model which is a fragment of a set theory, so think of R as either H theta for some theta or V theta for some theta. And you have an elementary submodel, and you have a cardinal gamma, and a set Z, which could be an ordinal, which is in M, and a function from Z to M, from Z to 2, 0, 1. This function is not in M, not necessarily in M. Now you say F is gamma approximated if the traces of that function to small sets, so sets of size less than gamma, which are in M, are in M. So small pieces of that function are in M, are known to you. So that's gamma approximated. And F is guessed in M if there is another function which is in M. So now F is not in M, but there is a function in M which agrees with F on the elements. I should have written Z intersection M, because the functions are from Z. Z is in M, but M is not transitive. So there are some elements of Z which are not in M, and F and F bar do not have to agree there. But on the elements which are in M, they do have. So this should be F restricted to Z intersection. Okay, so guessing M is a gamma guessing model if every function which is gamma approximated in M is actually guessed in M. So basically, if M knows pieces of the function f, then M knows the function f as far as what it does to elements of M. And this is the principle that I wanted to mention. So this is the statement that says that there are for in H theta, what is this? Yeah, there are stationary many gamma guessing models. So theta is arbitrarily large, sufficiently large cardinal. H theta is sets of heredity size less than theta. So this says that if you look at, and you have two parameters, kappa and gamma, but really we're interested in the case kappa is omega 2, gamma is omega 1. So just you can plug in kappa omega 2 and gamma omega 1. And it says there are stationary many omega 1 guessing models. The models are of size omega 1, and they are omega 1 guessing. And their intersection with omega 2 is an initial segment of omega 2. So this is the principle. And Viale and Weiss showed, oh, okay, so I'm going to kind of speed up a little bit. Gamma guessing, Aleph 0 guessing, it just means that any function which is finitely approximated in M is guessed in M, but that means every function is finitely approximated. So that just means that M is a second order elementary submodel of R. So every subset of a set in M is or every function from Z to any, if Z is an element of M and you have a function anywhere in R, which is finitely approximate, every function is finitely approximate, it is guessed. And then, so this is actually a reformulation of Magidor's characterization of supercompact. Kappa is supercompact if and only if this principle GM kappa Aleph 0 holds. And for this reason, we called models which are Aleph 0 guessing, we call them Magidor models. So if, for example, you are here, what it means, M is Aleph 0 guessing model, it means if you take the transitive collapse of M, you get some V delta bar. You get some V, some initial segment of the cumulative hierarchy. Now this principle that they studied, Viale and Weiss, is GM omega. They call it ISP, but we call it GM guessing models. They showed that PFA implies this principle, so there are enough guessing models. And this principle implies the failure of square, even square of lambda for all regular lambda bigger than or equal to omega 2. The three property Kruger, building on the work of Viale, shows that this principle implies the singular cardinal hypothesis. And Cox and Kruger showed that this principle is consistent with continuum arbitrary large. So this is a perfect principle for us to try to generalize. That's what I was trying to get to. And this is what we did with, okay, I'm going to skip, since I am kind of running out of time, I'm going to skip the notion of the approachability idea. It is another, I don't know if you know, it's a property, a combinatorial notion, an ideal on a regular cardinal lambda that was studied extensively by Schellach. And okay, so I'm going to skip this because and I'm going to get to the notion of a strong guessing model. And this will be almost at the end. So how do we generalize this principle? So which principle? The principle which says that there are stationary many omega 1 guessing models of size omega 1. Well, we say that the model is a strong omega 1 guessing model if it is, it's a size aleph 2, and it's a union of a chain of models of size aleph 1, each of which is a guessing omega 1 guessing model, and this chain is continuous at omega 1. This is the hard part. I mean, if you don't want continuity at omega 1 limits, you have it from PFA. But requiring continuity at omega 1 limits is extremely strong. And this principle that says that for given R is H theta or V theta. So you can just plug in V theta. And it says that there are stationary many models, strong guessing models. So models of size omega 2, which can be written as an increasing union of guessing models. But the key thing is that you have continuity at cof omega 1. This is a principle. Now, this principle, it actually implies that continuum is bigger than RF2. So you cannot have it. It's incompatible with PFA. But obviously, it implies the GM omega 2 omega 1, because it just says there are even more. I mean, there's, GM omega 2 omega 1 says there are stationary many guessing models of size omega 1. Now, here you say there are stationary many models of size omega 2, which each of them is a union of blah, blah, blah. And this implies this, the Mitchell's, but I skipped that. So the approachability ideal on omega 2 restricted to ordinals of cofinality omega 1 is the non-stationary idea, for those of you who know. So I'm going to skip that, but now let me tell you, with this approach, using just side conditions of two types, but which types? Countable models and what we call Magidor models. So we have to start with two supercompact cardinals, kappa and lambda, and we use kappa Magidor model. So what is a kappa Magidor model? It's an elementary, it's a model whose transitive collapse is some V gamma. And when I take the preimage of the collapse, it's the critical point is some kappa bar that gets mapped to kappa. It's like, what you get from Magidor's characterization of supercompact. So we use those models, and just, I didn't tell you the opposite, but using finite systems of models of these two types, which have the property that at every alpha, the relevant models are an epsilon alpha chain closed under meets. Then we get this principle, GM. So this is the work with my PhD student, former PhD student, Rahman Mohammadpur, who is coming here soon. And this has a lot of structural consequences. I will just let you read this. It's on the next slide. It's the consistency of this, but I just want to read some consequences. Continuum is at least aleph 3, there are no weak reparatory. This follows just from GM omega 2 omega 1. But you get simultaneously the 3 property at omega 2 and omega 3. You get the failure of squares, you get the singular cardinal. So this you get from GM omega 2 omega 1. But you also get this Mitchell thing. So basically, the idea is that you get some structural consequences of PFA that you had at aleph 2 from PFA. You get them both at aleph 2 and aleph 3. And the result is that it's consistent, just starting from 2 supercompact cardinal to have this. And this is done just by, it's not an iteration, it's just pure side conditions. That's what you get. Now, then you can start. So this is a sketch of this. I don't want to, I'm out of time actually. So then you can start adding working parts. Then things get quite complicated. So I'll just stop. I mean, it's work in progress. Thank you very much. Yes.
Yeah. Do you have one scenario for
Do I have any scenario for getting the effective CH? Yes. I mean, no, I don't, but I've heard the question and I plan to think about it. But I think it will be quite hard. You know, if you we have to. You start with very ambitious plans and you say, okay, now we have the side conditions, let's add the working parts. But even very modest, even we cannot, so what I wrote there, a bunch of things, if you want to add just the usual matrix axiom for CCC poses, it ruins you. We don't know how to do it. So you say, well, what's the problem? Because you will lose some properties of guessing models. So we are at a very, okay, so this is not an answer to your question, but what I'm saying is that we have to try to iterate very simple forcings first to develop some techniques. So I think we're very far from it. But I know the question.
Do you know how it is in your model?
What data of L of R?
Something like that.
I have not thought, but if you, what is L of R? I mean, yeah, I know. I'm just thinking. I think this should be, one should be able to figure it out, but it should be small. Okay, any more questions?
I have a question. So you were saying, I mean, so what would be the answer to CH if you have five forcing axioms?
Anything but CH, right? So
okay, is it going to be omega 3? Is it going to be omega 4?
But you know, then you have to decide whether you want to take the usual forcing axioms for Aleph1 or you want to take forcing axioms for Aleph2. They're going to be incompatible. But I'm hoping that you could somehow. I'm not going to answer the question. But that some kind of you have PFA or MM, and then you find a portion of MM that does not settle the continuum, and then you kind of push the continuum out.
So it continuum out of the universe?
No, I don't have a fixed theory. Yeah, I don't know. So your question is, what is going to be the value of the continuum? I don't want to say it's going to be RFE. I think it's going to be RF2, but this is a kind of alternative approach. What is the official consensus now? What is the continuum?
Depends what you like.
Yeah. No, so yeah.
Any other questions? Okay, so we can go on. You guys all coming for dinner?